Hello everyone, how are you doing? Yeah, I'm with my own magnifier today. Today I'm going to discuss about this, a simple microscope in the topic of optical instruments. Hello everyone and welcome to SMR Online Physics. I am Mahesh, your physics teacher. Let's have fun and learn how this simple converging lens, also called as a simple convex lens, actually really works out as a magnifier. I think everybody has enjoyed this device, right? So let's learn about it. Come on. So today we will learn about how a simple microscope actually works out and how much magnification can it produce, right? And why do we exactly need a microscope to see the things around? Because we already have a beautiful organ which can make us see the things around in crystal clear, right? In my previous classes, I've actually discussed about how a human eye actually works out. If you haven't watched it, do watch it. And I also discussed about the defects of vision in my last class. And in that, I discussed about a very important term called least distance of distinct vision, also simply called as the near point of a human eye. So for healthy grown-up adults, the near point, which is also the minimum most distance from the eye at which an object placed, can be seen clearly without any strain on the eyes, something like this. If this is at a comfortable distance of 25 centimeters, then I find to see very clear without providing any strain to my eyes. But if this object starts coming very close, all of you can definitely try that, the image actually goes blurred and fuzzy. Means there is a limit to the power of accommodation to your eye lens. But as the object actually goes away, again you'll see that you get an illusion like the size of the object's image formed on your retina goes on becoming smaller and smaller because the visual angle decreases. Now comes the point, what exactly is a visual angle for an eye? So what exactly happens is, when we see something, let me just give you a rough good idea about that. When you see something, there goes your eye lens, which can change its shape and size. That's what it's called as power of accommodation. And this is your imaginary principal axis, let us say that way. Now if the object is placed at the near point of an adult eye, which is considered to be equal to 25 centimeters and denoted by the alphabet capital D. So if this object is here, AB is the height of the object, and now you see that that's what is exactly happening, right? Yeah. So you'll find that this is the portion where the image is formed. You can understand what I mean to say, right? And this is what the angle is subtended by the eye onto the height of the object. This is what is called as the visual angle. But now as this object shifts away, far distance away, the height of the actual object is still the same. But what happens is the amount of light received by the eyes and making an image on the retina, this portion of the retina which gets illuminated by the light coming from the object has reduced, which makes us to see a smaller sized image of the same object. And now you can easily see that the visual angle has actually decreased. So theta is the visual angle, and the maximum angle it can subtend onto an object is when the object is placed at the near point. So when the object is placed at the near point, you get this maximum, the maximum angle subtended by the eye onto the object. We can call it theta, we can call it alpha, whatever you wish, not a big issue. So if I call it theta, then this tan theta is almost equivalent to theta because of its very small angle nature, and that is almost equal to the height of the object AB by the near point, that is the distance of minimum, better call it as least distance of distinct vision, better denoted by capital D. So I can say theta is equal to height of the object by 25 centimeters. So there is a maximum angle the eye can subtend onto an object. Now comes the point, what if I need to really see a magnified image even though the object is slightly closer? Because as the object comes closer, as I told you, you can always experiment by yourself, the image actually goes blurred out. But I want to see a magnified image of the same object. Can I do that? Can I increase this angle beyond this limit, which I said this is the max possible? Yes, that we can do with the help of let me get my magnifier. There you go. This is a simple converging lens, a convex lens, also very commonly called as a magnifying glass. And we have discussed about convex lenses in our previous classes. What kind of images it can form? It can form real as well as virtual images. The last position of the image, when the object is really closer, when the object becomes really close to the lens, something like this. Means if the object stands between the focus and the optical center of the lens, then the image actually becomes virtual, erect and magnified. So hence it is also called as the simplest magnifier or a simple microscope. Alright? Okay. So how it exactly works out, that is the main goal of today's class. So let me clean it off. Right. And there we go, how exactly it works out. So when I was actually seeing this object with my naked eye, something like this, yeah. This is what I get to see, clear. I bring it in between, yes. The image has gone magnified, okay. I think you people also can see that. If you see it from your point of view, maybe that way, right? Yeah, that is correct. That is correct. You'll get to see a magnified image. Alright? Okay, you can always try that. Okay? So how does a simple convex lens act as an excellent magnifier? How much it can exactly magnify? So we'll see something like this. Already I have shown this maximum angle which an eye can subtend. Let me keep it drawing here. I'd like to call that angle as theta. This is the height of the object, h, and this is your d, which is equal to 25 centimeters, and hence you see here tan theta equivalent to theta is AB by d. That's great. Alright, now if I bring in this magnifier into action, then you see this is a single convex lens. This is your principal axis. Let us say this is our optical center. This is the focus of the lens. And now if the object is placed slightly within the focal length of the lens, then you exactly know what is going to happen. The rays of light get refracted and pass through the other side of the lens. This is your focus. Again, the ray of light passes through the optical center. They do not intersect anywhere on that side, but rather they intersect somewhere here. So there you go, an image is formed of this object. So if this is A, this is my A dash and this is my B dash. So there you go, you get to see a virtual, erect and magnified image. So this is your object distance, which is lesser than the focal length of your lens. Let us call it UE. And this is the image distance formed. Let us call it as VE. So these light rays actually enter into the observer's eyes. Alright, my dear, right? So this is what exactly the person is getting to see a magnified, erect but virtual image. Alright? So let's do the simple calculation required for it. What we exactly need to do. So if I have to really calculate the angle subtended by the eye of this image, when this lens is placed in between, then you find the angle subtended is slightly increased. This angle, let us call it as beta. Alright? So what is the angle subtended over here? Because the angle is in fact very smaller, we can also call it tan beta, or simply call it as beta and take the trigonometric ratio, that is AB by UE. That is the object distance. This is AB, that is the height of the object. So this is H plus UE. So that's your beta and that's your theta. This is the angle subtended by the eye of the object when the object is placed at the minimum most distance, that is at the near point of the eye. And this is beta, the angle subtended onto the eye of the image formed. Of this object which is placed within the focal length of the eye lens. So be clear about this beta and theta. Alright. So now let's move on to calculate a new term. That new term is called angular magnification. You already know what is lateral magnification, M. But definitely you may not know what is angular magnification. Lateral magnification, let me remind you, that is the ratio of the height of the image to the height of the object. But now we are talking about the magnification produced by this lens onto the eye. So we introduce a new term that is called angular magnification. So I'd like to represent this angular magnification with capital M, trying to remind you that is all related with the angles. So m theta is always equal to beta by alpha. If you ever find it difficult to remember and not get confused, my idea will be as small m, lateral magnification was height of the image by height of the object. Same is the case. Angle subtended by the image onto the eye. First image, then by the object. But this alpha is the angle subtended onto the eye when the object is placed at the minimum most distance, that is at the near point. Be exactly clear about that. That is your beta by alpha. So let's find out what we can do from here. So m theta should be equal to, what is beta we got here? H by UE, and theta we got, sorry, I wrote here alpha, okay, excuse me, that was my theta. Theta is equals to AB by D, so H by D. Okay, please follow it carefully. So m theta should be equal to H by UE multiplied by D by H. So angular magnification is equals to D by UE. That's it. That's it. So this is also better to be remembered. 25 centimeters by UE. Okay, that's your angular magnification observed by this lens. So now let us consider two situations when the image exactly forms at the near point of your eye, and number two, when the image actually forms at infinity. When does the image form at infinity, my dear? When the object stands at the focal plane of the lens. Means the object distance becomes exactly equal to the focal length of the given lens. Okay, let's consider these two situations and find out the resultant equations. So let me rub it off. Come on. You'll always get a crystal clear explanation of the topic. No hurry burry, okay? No rushing around. So let's do that. So this is an expression I'd like to maintain over here. So case number one, I'd like to say when the image is formed at infinity. When the image is formed at infinity, definitely your eye lens is the most relaxed state. The ciliary muscles are relaxed when you're observing something really far. Okay? That is also called as unaccommodated state of your eye. So when the image is formed at infinity, that is only possible That is, it means automatically the object distance is exactly equal to the focal length of your eye lens. So what we get to see from there? What you will get to see, u is equals to Fe. How will you write the magnification right now? Very simple. So you can write m is equals to, you already have this equation, u is equal to Fe. So you will get the relation m theta is equals to d by Fe. That's it. Very simple. That was the case. ue is equals to Fe becomes equal to the focal length. So hence m theta is equals to d by Fe. As simple as that. So this is the magnification achieved when the object is placed exactly at the focal length or the focus of the convex lens, when the image actually forms very, very far, that is infinity. Now case number 2 is when the image is formed, okay, at the near point of the eye. At the near point of the eye means at a distance of d. That is equivalent to 25 centimeters all over the wall for a healthy adult eye. Alright? So that is the case when the image is formed at the near point of the eye. So how will you do that now? What does it mean like? Near point of the eye. When will the image form at the near point of the eye? When you have u is equal to, yes, ue, go to the back diagram which I just rubbed it off. Slightly within the focal length of your lens. You need to be slightly closer there. At the same time, the image distance, now you say it is equals to d. And the focal length is Fe, okay? The focal length of the lens you have chosen is Fe. So now you can quickly see that you need to put in the sign conventions, minus, minus, because both are forming to the left hand side and this is your plus. You understand the point, clear? Please go to the diagram which you have drawn, which I rubbed it off, which was here, right? So apply the lens formula, 1 minus 1 by u is equals to this, 1 by f, put in the numbers, 1 by v is minus d minus ue, this is equals to 1 by fe. What do you get here? Minus 1 by d, this is plus. So leave it over here and you can take it onto the right hand side. That's it. That is what you get. Do not go below that. Then you see that 1 by u e is equals to, if I take in something common like, okay, what I need to take common, if I take like 1 by d as common, then I'll find it is 1 plus d by fe. Alright, now if you observe, d by ue is equals to 1 plus d by fe. So what is d by ue, my dear? Still on the left side of your board, that use your angular magnification, so you'll get m theta is equals to 1 plus d by fe. So a single convex lens can do this much amount of magnification. When the object is placed exactly equal to the focal length of the lens, the image forms at infinity. This is your magnification. And when you really bring it a bit closer, that is what we exactly do like. I would like to always place the object within the focal length of the lens, and I really expect that the image forms at my own near point, that is at 25 centimeters, and hence you get an erect, virtual and magnified image. The magnification slightly improves. You can see that there is a difference of 1 plus d by fe. There is 1 plus of that magnification. That is what you get with a single lens. That may not be exactly enough. We will discuss upcoming the compound microscope, right? After doing simple microscope, which did not give us enough wanted magnification, means for example, I can't really see something too small with the help of a single lens. I need to compound the effect of a single lens by providing another similar kind of a lens. Another convex lens may be of different focal length. So when 2 or more lenses are arranged in a definite way, they can give you really an enlarged image, a magnified image. And that kind of a microscope, my students, I think you might have definitely seen in your school laboratories, right? Compound microscopes. Let's talk about how exactly a compound microscope magnifies a tiny object into really big size. Okay? The idea is very, very simple. Everything will be absolutely clear. Just follow the class. First of all you need a single convex lens, a convex lens of smaller aperture, smaller focal length. This is the lens which is going to be placed closer to the object. Right? This is the lens which is going to be placed closer to the object. So hence the name O. O will always remind you that this is also called as the objective of the compound microscope. Right. So it has a smaller focal length. Please mind it. I'll keep on reminding you by putting these FOs wherever necessary. So that will be indicating the focal length. So first of all, the object will be placed slightly beyond the focal length of this objective. So this is the object which I'll mark it as AB. Great. Now to compound this effect, because you know exactly where is this image going to form. The image is going to form beyond the focus of this, on the other side of the lens, beyond the focus. So it is going to look something like that. You just understand the beautiful diagram and everything happens very, very simple. That's it. That's one. Another ray of light passing right. Yes. Is my ray is going straight enough? Great, as always. So this is where the image is actually forming. Now this image will become an object. It's a real inverted magnified image of this object formed by this lens. Now this is going to act as an object for your second lens. So where is the second lens? That's coming up, placed at a certain distance with a lot of good calculations done. So yes, let us say this is the next lens. Is that good? Pretty good, yeah. This is your second convex lens which will be closer to the eye of the observer. So this is also called as E. E standing for eyepiece. Closer to the eye, so eyepiece, simple. This is your optical center. This is your P2. Yes. And now these rays of light which actually tend to come from here, no? This is the one. This is what you got here. This is the tip of the object. So this is your tip of the image, inverted B, B dash. Be careful, my dear. Come on. Now this is starting to behave like an object for the second lens which I call as eyepiece. So this lens is going to bend the light rays according to its abilities. Yeah. Now these light rays are going to finally enter into the observer's eyes. Yeah. That's it. That's the direction exactly. That's where the light rays are actually entering into the observer's eyes. So now when I produce them forward, you find that they meet somewhere very far. Let me get my diagram correct. Yes. And this is the tip of the object. Something like this. I hope I got it right, okay? Yeah, got it right, all good? Pretty much, without a scale. So this is the final image. The final image of this tiny object AB. This is the original object. This is the final thing what this observer is going to see. Definitely magnified, but virtual and erect. Please get the nature of the image very, very clear. So I should call this as A dash. So I will call it as A2. No more double dashes. And let us call this as B2. So this is your final image, my dear. That's it. Everything is clear? Good. So let us say this is your object distance for this. So I call it as UO. O will remind me object. At the same time, this tiny distance is the focal length of this object objective. There is F naught. And where is the image? Yes, this is the image. This is the image of the object formed by the first lens. So let us call it as V naught. Everything is in the diagram, nothing else to do mathematically. Come on. Now this object is placed in such a way, this image is formed and this lens is adjusted in such a way that actually forms within the focal length of this length. So I should call this as FE. So this is the focal length. This is the focal length of your eyepiece, FE. What about this distance? This has to be exactly your object distance from the eyepiece. Not to be getting confused with a lot of dotted lines. I'm very, very sure everything's clear. So this is your final image distance, VE, formed by the eyepiece. That's it. So once you're damn sure about the diagram, finish, you can get it always right. Okay? So now we'll start comparing what is the angular magnification maximum achieved by this compound microscope. So for that to happen, first of all I need to recall what is the maximum angle subtended by an eye when the object is placed. I will now mark it as alpha, okay? Previously I called it theta, not an issue. So this is your object, the tiny object. So this is your height of the object and this is D is equals to 25 centimeters. So from here we already found that alpha is equals to AB by D. That's it. That's the maximum angle without any sort of help. Your eye can subtend onto an object very comfortably, right? So now everything has come up like this. Now those who have followed this part very carefully, they will find it definitely very, very easy like. So what is the angular magnification? Therefore, m theta, angular magnification, same thing, beta by alpha. Where is the beta in the diagram? Yes, this is your beta. Observed? This is the object for this lens and hence it becomes the angle subtended by this eye of this actual object. This is where the image is formed. Great, let's get on to it. So let us put in what we exactly know. M theta is equal to beta, you observe closely, this tiny triangle. So I can say the ratio is A dash B dash, A dash B dash minus sign. Don't forget the sign convention, that's the tricky part. Upside down image by this base is equal to UE, okay? That is minus UE because the object is on the left hand side for this lens. What is alpha? Great. This is AB, positively up. This is AB. And this is D. Again, from the left side. So you get a minus D. So, 3 minuses. So, 2 will be out. And you will be left with minus A dash B dash by AB multiplied with D on the top and UE at the bottom. Simple, clear, come on. Come on. Yeah. Now we will find out what are those two terms and let us put it in. Simple. I'm making sure you have noted this diagram, okay? So from the figure, we have two triangles which are similar. That is ABP. You see this angle subtended? And A dash B dash P1. This angle. So this angle and this angle is same. This angle is same, 90 degrees. So triangle ABP1 is very, very similar to triangle A dash B dash P1. Come on, right? So these two triangles are similar, so I can say A dash B dash by AB should be equal to P1B dash by P1B. Simple. Okay, what I get from here, this is what I exactly have it over there. What is P1B dash? P1B dash, right side. This is my image distance V0. And what is P1B? P1B is on the left side. So this is your minus U0. So this part of the ratio, you are now very sure what you exactly got it like. P1B dash positive V0. This is negative of U0. Great. Okay, what else we have? The next part. Now for the eye lens, my dear, for the eye lens, let us write it down. I'm writing out of space. I will write it here. For the eyepiece, that is a much more clear term for all of you now. For the eyepiece, if you observe, what is your object distance? What's your object distance for the eyepiece? UE. So it should be minus UE, no doubt. What is the image distance for the eyepiece? This part. This is VE, so it is minus VE. Great. Anything else you want to know? The focal length, definitely. Focal length is plus FE. So using the thin lens formula, okay, this is an approximation. Thin lens formula works out. So you put in this thin lens formula clearly and you'll find 1 by minus VE minus UE is equals to 1 by FE. Is that good? So you will find ultimately 1 by UE is equals to 1 by FE plus 1 by VE. Right. So we got this. We got the value of 1 by UE. This value of 1 by UE, I'm going to put it over here for the term angular magnification. Please note it down so that I can rub off certain part of it. Most importantly, I need to rub off the diagram. Come on. Can we do that? Right. I really don't want to rub off the diagram, but I have no choice. Make it sure you have seen everything clear, okay? Right. I rub off the diagram and there we go. Now I'll finish it off. So I substitute this value, okay? Substitute this value here. Hence, we will get m theta is equal to a dash b dash. Where is that? This one. That is minus already there, and this is coming again as minus there. So you get something V0 minus U0 multiplied with D. Where is the D? D is there. And this is your 1 by UE. So that comes out as 1 by FE plus 1 by VE. Okay, are we all going good and great? No issues with sign conventions. Anyway, the diagram is gone. P1B dash, right side. P1B on the left side. All good. Right, minus, yeah. So I can now readjust this entire thing and I'll find here V0 by U0. Something fishy over here. Let us see what we get. If I take 1 by V common there, it becomes D by VE 1 plus VE by FE. That's it. That's your term for angular magnification, right? So everything good and great? Yeah. I'm finding something fishy. Let me just take it once. Right. Yeah, we do not exactly need to put a minus sign. This is always plus. Okay? Because we have already used the sign convention. So here it is not required. So ultimately it comes out to be minus. That's it. So that's your angular magnification by a compound microscope. Alright? So now there can be two possible adjustments of your microscope's lenses to make your view much more clearer, comfortable, and you get a magnified virtual image. So the first possible adjustment can be case 1. when the image is adjusted to be formed at infinity. So when the image tends to be formed at infinity, what is the case? When the image tends to be formed at infinity, it means that image distance has turned out to be infinity. Alright? So I mean to say image distance, this is the case, VE should be equal to infinity. If I put in the infinity over there, VE should be equal to infinity, then you'll find the angular magnification achieved by the compound microscope will be equal to minus V naught by U naught, make it sure, multiplied by infinity, that's gone. So ultimately you're left with D by F. So it almost looks like this is also sometimes written as the total overall angular magnification achieved by a compound microscope is a product of the magnification achieved by the objective multiplied by the magnification achieved by the eyepiece. Great. Okay, that is one case. Let me put a bar over here and then cross it over. And the case number 2 possible is when the image is formed at the near point of the eye. When the image is formed at the near point of the eye, that is at D is equals to 25 centimeters. Then you'll find what will happen then? Come on. So VE itself will become equal to D. That is equal to 25 centimeters. Look at the equation. Therefore, I should find m theta, the angular magnification should be equal to minus V naught by U naught. This is gone, you see this? This is gone. So you will be left with 1 plus VE by F. This is again D there. So that's it. Into 1 plus D by FE. So again you can get to see that m theta can be always written as a product of magnification achieved by the objective multiplied by the magnification achieved by the eyepiece. That's it. So those are the two possible beautiful cases where the images can be adjusted to be formed. Okay. So this is your magnification achieved when the image is formed at near point of the eye. That is at D, 25 centimeters. And this is the magnification achieved when the image is adjusted to be formed at infinity. Right. Am I clear? Now also this magnification can be also shown in the in terms of the distance between the two lengths. Let us see that how it looks like. So let me remind myself this equation over here. M theta is minus V naught by U naught into D by VE plus VE by FE. Okay, right. So let me rub it off. Are you enjoying class? Are you enjoying the class? Come on, have you understood it clear? Give me a thumbs up, okay? Give me a like, right? And please do not forget to share your comments in the comment section below. Great? Okay. Now in terms of the length, means what I was showing you, most of the times the objective is really a small lens with a very small focal length. This is the one objective, and on the other hand you had this eyepiece. So they are adjusted and done in such a way that this length can also be helping us to find out what is the overall angular magnification. This is the L between them. Alright? So how to really do that? So for the objective being of very small focal length, V naught by F naught can be much greater than 1. Yeah, F naught can be really small, so the ratio of V naught by F naught can be much larger than 1. and the image will be very, very close to formed. It will be very close to the eyepiece. So you can also approximate V naught almost equal to the distance between the two lenses. This is my eyepiece. Great. So what we can do it like, now we can write for this objective 1 by V naught minus 1 by U naught is equals to 1 by F. So instead of directly writing it off, I can also show you now in the second step with the sign conventions correctly. This is V naught positive, this is minus U naught, this is equals to 1 by Fe. All clear? Come on. So let us quickly see what we get here. 1 by V naught plus 1 by U naught is equals to 1 by Fe. That's equals to 1 by U naught is equals to 1 by Fe minus 1 by V naught. So if I happen to take the ratio, that will be great, isn't it? Instead of doing this, let me take a ratio here itself. Take a common 1 by V naught, you get 1 plus V naught by U naught. That's it. What you'll find here, I'm writing Fe, my dear. This is F naught here. Okay. So 1 plus certain times it happens like V naught by F. Yeah. So what you get to see here, this is what I say, much larger than 1. So we can now write V naught by F naught minus 1 should be equal to V naught by U naught. So this is definitely larger than 1. So hence I can say V naught approximated to L. So we can say V naught by U naught can be equivalent to L by F naught. This is really a good approximation for thin lenses. In reality, the thin lenses are not that thin. Okay? This is a good approximation to understand the working of a compound microscope. Hope I am clear. Okay? Great. So if V naught by U naught by this is the case, then we can go for the first case now. That we got the first case, M naught is equals to, you see the formula? There's a minus over there, V naught by U naught, you got it there. Minus L by F naught multiplied by D by Fe. For which position this is true? When the image is formed at infinity. So this is another beautiful expression in terms of the distance between the two lenses of a compound microscope. On the other hand, number 2, M theta can be written as, again the same thing, minus L by F naught. This is equal, so that is equal to into 1 plus D by Fe. This was true when the image forms at the near point of the human eye. So those are two dear expressions in terms of length, that is the distance between the two lenses. So please do watch it carefully, practice the diagram carefully, learn it properly. If you have any issues, any doubts, any comments, feel free to ask me in the comment section. And if you're new to this channel and if you like this video, do like it, share it and subscribe for more interesting physics videos. Thank you. Have a great time ahead. And next time I'll expect you once again to watch my classes, right? See you again. Bye-bye. Thank you.